During the last lecture, where I left you, if you remember, that I have tried to establish some or write some balance equations, material conservation equation, and in that context, towards the end of the lecture, I have shown that I have altogether written about 11 variables, input parameters as well as various blast furnace operating parameters. And of those, if you look back at your notes or try to recapitulate, you will see that I said categorically that 4 of these variables are basically given to us. That is the input of iron and output of iron, because output of iron is 1 mole. So accordingly, input is known. Similarly, the ore composition O by Fex is known, as well as the C by Fe, that is the carbon content dissolved, that is dissolved in molten iron or hot metal, is also known. And that left us with 7. And the last statement that I have made during my last lecture before leaving this room was that, if 3 parameters can be specified, then all these 7 unknowns can be calculated. And those 3 parameters are basically NaC or NGC, O by C gas, as well as NOB. This is the active carbon. I have defined what is the active carbon, or the carbon which is there in gas phase. And all these terms, I repeat again, that these terms are all par on the basis of per mole of iron Fe produced. Okay? So if you say NaC, there is a number of moles of carbon in the gas phase per mole of Fe produced. Similarly, NOB, number of moles of oxygen, where not O2 but O is our basis, number of moles of oxygen in the blast per mole of Fe in the product. So likewise, and O by C is the oxygen to carbon ratio in the top gas. So if these 3 parameters can be given to us, if we can calculate, then we should have the coke rate, we should have the top gas composition, we should have the blast rate, or how much of blast will be needed under steady state operation. This essentially tells us that we need to have 3 equations to calculate these 3 variables. And once we have 3 equations, we can then say we will be able to calculate 3 parameters. So these are now my model parameters, or the key blast furnace operating parameters, and these can be calculated on the basis of 3 equations. So if I can establish 3 equations, in that case I will say that I have a fully predictive blast furnace operating model, which will be valid under the steady state operating condition. So it is to this the development of the 3 model equations we will be now concerned with, and the next few lectures I will outline the derivation of the 3 equations. And if you remember that if I said N input of oxygen, so this is I is input of oxygen, oxygen is there, and this is again per mole of oxygen, okay, per mole of Fe, and this is NBO, which is the oxygen in the blast, and this is O by Fex. That's what is the oxygen input. And we are talking about, as of now, an idealized blast furnace operation where there is no gangue material, so there is no lime charge, there is no. I want to illustrate the concept first, and then I will show that how, built on this elementary simplified model, we can add module after module, or we can incorporate all sorts of complexities. It is understood clearly that the input of oxygen will vary depending on the raw materials. So when we do not have any impurities present, gangue materials present, it is the oxygen is coming only from the ore, and oxygen is being supplied from the blast itself. There is no silica reduction, there is no amino reduction, there is no P2O5 reduction, so there is no contribution of metalloid reduction on this oxygen input. But in real blast furnace, we will have additional terms, okay, on top of these 2 terms which I have listed. Then that you must remember, and we will see as we advance and make our simplified model adaptable to actual blast furnace operation, we will see that how these elements can be added, or the components can be added to the oxygen input, carbon input, and so on and so forth. For example, limestone dissociation will contribute to carbon production in the blast furnace, or a source of carbon, because carbon dioxide will be coming through it. So, similar concepts can be. I have also told you that we have NiC, the input of carbon, which is equal to NaC, the active carbon, plus C by FEM. Since this parameter is known and this parameter is known, okay, this is given to be varying between 0.20 to 0.24 depending on what is the composition of the hot metal. And I have told you yesterday that if you disregard silicon etc. to be present in the hot metal and assume that it is 4.3 wet percentage carbon dissolved in iron, then C by Fe comes out to be only carbon saturated hot metal containing no other impurities, the C by Fe ratio will come out to be 0.21. Similarly, if you have hematite iron ore, we will have O by Fex. Considering that O and not O2 is the molar basis of oxygen considered in this discussion, this value will come out to be 1.5. This is a function or characteristics of the ore material that we introduce. So this could assume a different value. If we suppose if we use metallic iron as the charge and some FeO as the charge as well as some Fe2O3. So suppose we have direct reduced iron where we may have Fe2O3, we may have some Fe and we may have some FeO. So if we charge direct reduced iron in a iron blast furnace, this value could be significantly lower than 1.5, which is the value for hematite, and so on and so forth. So all these variations of iron bearing materials can be accommodated through an O by Fe, which can be calculated depending on that what is the composition of the DRI that is being charged in, or in what proportion we will be mixing various iron bearing materials and so on and so forth. So the input of carbon can be calculated once the active carbon is calculated. Similarly, the input of oxygen can be calculated. So the two parameters will explicitly give us the input of iron and input of carbon. What about the output of iron? The output of oxygen, the oxygen is in the gas phase, and yesterday I have said that the output of oxygen can be written in terms of the O by C in the gas phase, and I have said that in the carbonaceous portion I have shown you of the gas we have this relationship 1 minus O by C. So once the top part of top gas composition is so if we add this up, I think it is O by C minus 1, O by C minus 1, and this is 2 minus O by C. 2 minus O by C. So if you add this up, x CO2 plus x CO, and then we will say this side becomes this and this will cancel out, and this will give you 1, because we are talking about only the carbonaceous portion of the gas. So this relationship is valid. Once you know the O by C gas composition and the top gas in the carbonaceous part, we will be able to calculate explicitly the composition of the gases. This is a composition and O by C relationship. And this equation tells us the output can be calculated, provided already I have calculated from input, because input of carbon I have somehow calculated. So NaC is known, and if NaC is known, I require to calculate. So the input of oxygen will be known from the blast of oxygen in the blast. Output of oxygen will be known from the coke rate as well as the top gas composition, and similarly the NaC will tell us that added to C by FEM will give us the NiC. So these are basically the three principal model parameters that we aim to calculate. With this, I will now go and write the overall oxygen balance equation in the blast furnace. Overall oxygen balance. I have made a series of assumptions. I will categorically show now that with a line drawing that what it is. So we have feed here, which is Fe2O3. We have carbon here, no coke, pure carbon, okay. And then we have blast here, we have exit gas here. And that contains CO, CO2, I do not know, and nitrogen, ideal speaking. We have hot metal here, and that hot metal contains only 4.3 weight percentage carbon. That is the scenario we are talking about, and the rate of input here is NBO. This is, I have NIC, the variable, how much of carbon. I know that I want to produce 1 mole of hot Fe, so I know half a mole of Fe2O3 is to be charged. I do not know this, and this has a characteristics of O by C gas that also needs to be determined. This also needs to be determined, and this also needs to be determined. So that is basically an explanation under which the oxygen balance equation will be written, okay? And therefore, I can write input of oxygen is equal to output of oxygen under steady state condition, and therefore I will write that NOB plus 1.5 is equal to NaC and O by C gas, as far as whatever I have shown. So this is my overall oxygen balance equation. Now, for example, if I just add one single parameter, I say that look, I have, in addition to 4.3% carbon, I have some silicon in the hot metal also, 1 weight percent silicon. So I can, just like the way I have determined C by Fe, I can calculate Si by molar ratio of in the hot metal. In the metal phase, I should be able to calculate molar ratio of silicon to Fe, also given the composition that my hot metal, my target hot metal composition should not contain anything other than 1 weight percent silicon. So I will be able to say that if you take 100 kg, 4.3 kg is carbon, 1 kg is silicon. So 1 divided by 28 and 90, this is 5.3, so that means it is 94.7, so therefore 94.7. So this will basically be equal to 1 divided by 28, and this is going to be 94.7, okay. So 4.3 plus 1, 5.3, so that makes it, and this is what? That's what it is basically for this particular scenario. And we know that if entire amount of silicon present has manifested in the hot metal, this is an ideal case, silicon will partition, and we will see that what's the consequence of silicon participation later on, but I just want to show you that how you modify so the equation. So therefore, once we say that this parameter, given the composition, this parameter is known, so I can say that if silica undergoes reduction, so it should contribute to 2O. Every mole of silicon per mole of iron, okay, will contribute to 2O. So therefore, if I multiply, this will give me the oxygen which has been released because of 1 weight percentage silicon in the hot metal itself. So factor of 2 multiplied by. So this parameter, this is determined from the stoichiometry of the equation, and this is determined on the basis of the given composition itself. And then we can say that look, this equation under the given condition that 100% of the silica gets reduced and yields 1 weight percentage hot metal. So therefore, the equation will be very well given in terms of 2 multiplied by 1 by 28 divided by 94.7 divided by 56 plus 1.5 is equal to NaC and O by C gas. Note that this NaC and this NaC are not identical. This O by C and this O by C is not identical, because the reduction of silica will require some amount of additional heat. So, therefore, the carbon rate will go up. Similarly, oxygen which is released because of the reduction of silica will change the O by C ratio, and as a result of which both these parameters. So, I should have written this is A prime, but I will not write that, okay, just to show that these parameters are now different when we have case 2 100% silica reduction leading producing 1 wet percentage silicon in the hot metal itself. So, just like I have incorporated silicon, one can incorporate phosphorus reduction, one can incorporate manganese reduction, and so on. Whatever produces oxygen needs to be accommodated. If you have, we will see that when you have oxygen enrichment, this NOB value will get, the total blast value will change, blast rate is going to be changing because the oxygen to nitrogen proportion are going to be changed also. So, some modification will be necessary. So, all those parameters which are going to contribute to oxygen change input into the system can be taken into account, and that input is going to now be manifested in the output in terms of both, reflected both in terms of the coke rate as well as O by C gas composition. Now, let us look at that equation. So, we will be doing all this. I just wanted to demonstrate that Sir has written an equation for an idealized condition of blast furnace, no impurity, etc. If you have impurity, then how the equation will look like. So, I have just shown as a typical example that taking one single complexity into the process, but you can keep on building one after another terms depending on what sort of a physics you want to take, embody in the overall oxygen balance equation. So, let us consider. So, ideal blast furnace operation NOB 1.5 and is equal to NaC into O by C gas. Now, these terms, as you can see, this is an oxygen balance equation, overall oxygen balance equation as I have written. These terms are the oxygen which is present per mole of iron coming from the ore, and this is the blast oxygen which is also per mole of the ore, and this is also the total oxygen in the gas phase which is also per mole of the ore. So, now what we can see that this is a measure of O by C is a measure of the oxygen which is present in the gas phase itself. So, we can visualize this, we can write this as 1.5 minus NOB. We want to graphically represent it, okay, and then we can write it like NaC into O by C gas minus 0. This also can be written like this. So, we want to cast it in the form of Y2 minus Y1 is equal to m into x2 minus x1, where x1 y1 is equal to, if you can look at it, x1 y1 is going to be equal to 0 comma minus NOB, and x2 y2 is going to be equal to, what is that? X2 is going to be O by C gas comma 1.5. So, what we are going to plot? We are going to plot on the ordinate y, what is there? Oxygen per mole of Fe. So, this is our oxygen per mole of Fe. That is what it is, per mole of. And x, what we are plotting here is the O by C ratio in the gas phase, and as I have indicated that the O by C ratio can have a value, will have a value between 1 and 2, it cannot go somewhere. Now, x1 y1, if you look at it, 0 and NOB, this is 1 point, and 0 and NOB minus NOB, this essentially represents this particular point. So, this is 0 comma minus NOB. Now, the second point tells us that it is equal to 1.5 here, and somewhere if this is 1.5, and then we can say that whatever is the O by C ratio, let us say that this point essentially represents therefore, I would say x2 y2. So, this is equal to O by C gas comma 1.5, and then we get this line. We join these two lines, and that is what it essentially represents. And the slope of this line, is a measure of NAC. That is the graphical representation of this particular line. Okay. So, the overall oxygen balance equation can be converted also in terms of a plot between oxygen per mole of Fe, and where we can see that this is the oxygen which is present from the ore, and this is the oxygen which is supplied from the blast. So, this is the supply, this is a measure of the supply of oxygen, and this is inherently present in the system, okay? And this value will change 1.5 as I have indicated, depending on whether what kind of an ore you are using, what kind of an iron bearing material mix you are using, or what kind of an impurity are there. So, this value 1.5, for idealized case it is 1.5, but when you have a non-ideal case, do not consider this point to be 1.5, it is to be calculated just like the way I have shown it on the extreme right side of the board. And then you must understand that as the O by C ratio, is going to be changing. So, if the line, therefore, a higher, that is what I have already said, that if the line tilts to a lesser slope means lesser coke rate, and therefore, we have more and more CO2. This 1 essentially means O by C is equal to 1 essentially means 100% CO point, and this is 100% CO2 point. So, as the line shifts, or the slope becomes less steeper, in that case you have more carbon dioxide, and that essentially is reflected here, that the slope of the line will change, therefore the coke rate is going to be decreased, and which shows that the furnace is operating at a higher efficiency, because the slope of the line, the coke rate is small, and the gas contains more carbon dioxide. That means all the carbon monoxide which are ascending from the 2 air region has actually taken part in the reduction reactions, and in turn have oxidized and into CO2 and manifested in the exit gas, with a large volume of CO2 relative to the volume of CO. So, it is understood that this equation is not fully predictive, because there are 3 variables. I will have to give you, I will say that in a blast furnace operation, my coke rate is so much, idealized blast furnace operation, the top gas composition is 20, 30 or 30% CO and 40% CO2 or something like that. So, if I give these 2 parameters, you will be able to calculate the blast parameters, but that is not the objective. We want to develop a fully predictive model. So, that means we have to now look for additional equations, 2 other equations, such that we can have overall oxygen balance equation coupled with 2 other equations, and thus form 3 equations, 3 unknowns, and hence conclude that we have a description that a mathematical description that is completely or fully predictive. The second equation that we right now derive, these 2 equations are very simple. The third equation is going to be a little bit complicated. We will say that the bottom segment oxygen balance equation. So, this is our equation 1, you must remember, NOB plus 1.5 for idealized blast furnace operation containing pure Fe2O3 as iron bearing material and no gangue material present whatsoever. The overall oxygen balance and the hot metal containing 4.3% carbon, this is the overall oxygen balance equation. And now we have to consider the development of the second equation, and that second equation is, we will call that overall oxygen balance equation is this, the bottom segment oxygen balance equation. So, let us draw the blast furnace. What is that bottom segment I want to clarify? Now, we are dealing, if you remember, with steady state material and enthalpy balance. That is we must remember. Now, when you say bottom segment, we will compartmentalize the blast furnace into 2 halves. Where is, so this is I call it as a CLD or conceptual line of division. Line of division. Per se, there is nothing like a line of division because things are smudged. There is no, as sharp as it is, try to implicate through this hatched line as I have drawn on the board. So it is for the sake of conceptual, and we will make some idealizations also, and but it is a good representation, the lower upper part as well as the lower part of the blast furnace. And we have still the same thing continues, the ideal discussion, Fe2O3, pure carbon, off gas, CO2, N2, blast, NOB, hot metal, 4.3% carbon. That is what it is, which is the parameter here is O by C gas. The parameter here is NaC or NiC, and this is or NiC, and this is our second parameter here, and this is our third parameter here. We have divided the blast furnace into two parts. The moment we divide, and it is a steady state operation, we must understand for any variable, any species that we are doing material balance, I can say that the output of any species X, whether it is carbon, whether it is iron, whether it is oxygen, from the upper segment must be equal to the input of X into the lower segment. Continuity of mass and heat flow across the conception, that you must respect, and then you can put this line anywhere you want, but we will show you where that conceptual line of division is located in the blast furnace. This is the bottom segment. That continuity must be respected. And then this conceptual line can be placed anywhere you want, but we will place it at a suitable location. I will tell you that where is that location. The conceptual line of division is, divides the furnace into two different halves. This is the upper half where we apply that the temperature here is much smaller. So it is only that higher oxides of iron, this can get reduced to Fe2O3, this can get reduced to FeO, and there is so in this case what happens is we have this is Fe3O4, okay, and then we have Fe3O4 to Fu. This reduction reactions can take place. There is a higher oxides can get reduced. This, because the temperature in the upper segment is smaller and the temperature in the lower segment is greater. So we will say based on this temperature criteria we will draw this line. So we find out that we say that in the upper part it is only this oxides which can reduce, but FeO cannot be reduced, okay, because the temperature is too small. In that context, you must remember that I want to, before I proceed further, I want to clarify one thing, that Fe2O3 we call it as hematite, Fe3O4 we call it as magnetite, and FeO we call it as austite. Truly speaking, FeO is an iron deficient. The actual correct formula is, this is the correct formula. And we are going to use this formula and not this formula, which is good for discussion of undergraduate stoichiometry or undergraduate some kind of a small calculations not involving huge quantities. So approximation of like this is good for maybe high school work or something like that, but not for iron making. And yesterday I have made the statement that all the variables we will like to compute till the third decimal places because of the magnitude of the parameters when translated to the actual operating measures. So therefore, since we will be talking about per day 13,000 tons of Fe produced, so Fe, okay, and Fe 0.947 will make an enormous difference. So we should be using an exact prescription. So the Oostite we will try to represent not as FeO but as Fe 0.947. Oostite is an iron deficient compound. Iron deficient compound, it is seen the 1:1 stoichiometry is not maintained here, and there are some vacant sites in the lattice, and that is why we say some iron atoms are missing. If iron atoms are missing, in that case how the electrical neutrality is maintained? The electrical neutrality is maintained that we have somewhere, instead of Fe2 ion, Fe3 ions are located, and that is how the electrical neutrality is maintained. So it is a mixture of Fe2 ion plus Fe3 ion, and also it has a lot of vacant sites. Okay? So that is why it is called an iron. If you do not know, this is for you to note that everywhere when we write, the final stage of reduction of iron ore, we will write this reaction plus CO, and then we will say that this is equal to 1.06 Fe. So if we write 1.06, then if you want to get 1 mole of Fe, and that is what you are going to get, plus you can get if 1.06, so we will get 1.06 here, so we will get 1.06 CO2. To produce 1 mole of Fe, we have to charge 1.06, because 1.06 multiplied by 0.947 will give you 1. Okay? So 1 mole of Fe, to produce 1 mole of Fe, we will require 1.06 moles of Oostite. So these reduction reactions are possible, and these reactions are possible means we are talking about only the gaseous reduction reaction, gaseous reduction of Fe2O3 to Fe3O4, gaseous reduction, or gaseous reduction means reduction by carbon monoxide gas of Fe3O4 to FeO, that is possible. In this part, because all silica reduction etc., these are extremely high temperature process, extremely endothermic reactions, so they will never happen here also. Also we have seen that we have a gasification reaction, carbon solid plus CO2 is equal to gas is equal to 2CO. This is an endothermic reaction, and this will occur at the lower part. So there is no gasification reaction, and actually if you look at, if carbon monoxide is only taking part, if reduction reaction whatsoever is taking place in the upper part is owing to entirely because of gaseous reduction, and that metalloid reduction reactions, that gasification reactions are absent totally here. Therefore, I can conclude that whatever carbon I have charged here, that carbon will descend and enter this line, conceptual line of division. If I put this conceptual line of division here, I cannot make that statement, okay, because there will be gasification reaction. So in this reaction, so conceptual line of division is placed at a place above which gasification reaction is absent, metalloid reduction reaction is absent, and only reduction of higher oxides of irons are taking place here, and these reductions are not direct reductions but indirect reductions. Okay? And if we now apply this hypothesis, then we can, a corollary comes out that if this is true, these are the hypotheses, based on that we can conclude that whatever carbon therefore is charged, or coke therefore is charged into the blast furnace, that coke is behaving as an inert species here. In this case, what is happening? Mere redistribution of carbon monoxide and carbon dioxide is taking place. It is only carbon monoxide which is, as a result of which ratio of carbon monoxide to carbon dioxide will be changing here, but the total mole of carbon in the gas which is living here and must be same as the total mole of carbon which is manifesting here, but the relative proportion of carbon monoxide and carbon dioxide here and carbon dioxide monoxide here are not going to be identical, because reduction reactions, gaseous reduction reactions are taking place. But I repeat again that the moles of carbon leaving this conceptual line of division is exactly the moles of carbon, and this tells us that this has been possible because of the fact that we have set up this line of division in such a way that we have made carbon inert, that the charged carbon does not take part into any of the reactions. So therefore, this is the region which you call as the upper segment of the blast furnace, and this is the segment, this is a relatively lower part and this is relatively upper part, and we can safely say that this reduction reaction really, the gasification reactions, the gasification reactions and the Oostheid reduction reaction really does not take place. They take place 500 degree, 300 degree, 400 degree. As I said, Fe2O3 will get reduced in no time even at 300 degree centigrade. Okay? Fe3O4 a little bit higher temperature, 400, 500. But reduction of this will never happen before 900 degree centigrade. Okay? And that I am saying that this reduction reaction is not possible in the upper part, it is possible in the lower part. So, a limiting position of the conceptual line of division can be put at 900 plus 273, that is about 1200 Kelvin. There are various advantages that we will see later on for this. So, I hope it is clear to you that on what basis that before this above temperature is lower here, and in this region this reaction is not possible. It comes out to be 900 plus 273, 1173, but for the sake of because these lines are nevertheless not so sacrosanct in a blast furnace operation, we are making idealization, and as I said, models are built up on certain idealizations, and this is one of the idealization that we have rounded off the value of 1173 to about 1200 degree centigrade. You can now see that the moment a corollary comes, that if the blast temperature is any temperature, suppose we put in, okay, the blast will get heated up and then it is going to leave at 1200 Kelvin, because this is the temperature of the conceptual line of division, assuming that everything below is 1200 and above is less than 1200. So, whatever gas is going to be leaving this is going to be leaving at 1200, because that is the boundary temperature. So, it is immediately understood that if the temperature of the blast is 1200 degree centigrade, that means the blast will be not taking away any part of the sensible heat with it as it leaves the Oostheid reduction zone. Or to the bottom segment, I would say, if the temperature of the blast is more than 1200 degree centigrade, then the blast is going to yield heat to the bottom segment. On the other hand, if the blast temperature is going to be smaller than 1200 Kelvin, in that case the blast is going to be absorbing heat from the bottom segment itself. So, the blast, as you can see from a thermal point of view, can contribute heat to the bottom segment, which will come in a greater detail when we talk of the enthalpy balance, bottom segment enthalpy balance, but just I thought that these are interrelated. So, I would introduce this point also and sensitize you about the role of the blast in terms of supply of enthalpy into the bottom segment. So, therefore, this line can be considered to be at 1200 degree, and below this temperature only limestone calcination, this is 900, this is basically approximately 900 degree centigrade, and it is here that below this where the temperature is more intense, we have Oostheid reduction zone, Oostheid reduction taking place, we have gasification reaction taking place, okay, and we have all other endothermic reactions are taking place. Now, that this line below this line of Oostheid reduction is taking place, this bottom segment is also termed as Oostheid reduction zone oxygen balance equation. So, I can write bottom segment of oxygen balance equation or WRZ Oostheid reduction zone oxygen balance equation, that is also possible because it is going to be. Now, let me just quickly erase the board here and then show you what is happening, so that I do not have to draw the diagram again. So, this is my conceptual line of division. If we take into this, we will see that whatever was the overall blast parameter NOB is identical for the top segment, for the entire blast furnace as well as for the bottom segment. Also, we will see that this NIC, we are going to see that the same carbon is going to be coming in. So, this overall furnace parameter, this NIC, NOB, these are overall furnace parameter, okay, O by C. NIC is also going to be applicable to the bottom segment. The input of carbon because carbon is inert here, as I have been repeatedly saying, okay, because of the assumptions that I have made, because this temperature is smaller. So, as a result of which, whatever carbon is put into the furnace, the same amount of carbon is also coming into the bottom segment of the furnace itself. So, the NIC continues to apply, and that the metal will always contain 4.3% carbon. That means you can say that NGC evaluated for the entire furnace and the NGC in the gas phase are going to be absolutely identical, but the O by C value is not going to be identical, because there is redistribution of carbon monoxide which will take place. So, I can say that the oxygen which is GO, the parameter, in terms of this exit gas, the exit gas will still contain CO, CO2 and nitrogen, and then it will have an O by C value, and if this is the O by C for the overall furnace parameter, then I will say this is the O by C of Oostite reduction zone. That is going to be different, because the proportion of carbon monoxide and carbon dioxide that determines the O by C, and because the reduction reaction is taking place, so therefore the proportion of carbon monoxide and carbon dioxide are changing here, and as a result of which this value cannot be same as this value. Okay, we will see what this value is in a minute. So, therefore, the overall this parameter, whether it is upper segment or common parameters, upper segment and bottom segment, in the upper segment iron comes as Fe2O3, but here in what form iron comes? The iron comes as Oostite. That is what is prevalent in this part. There is no higher oxides which can remain here. So, since the Oostite formula is shown to be 0.947, it is understood that for every mole of Fe produced, because that is my basis of calculation, I must say that the iron bearing material here is Fe0947. That is my iron bearing material that comes into the furnace. So, the same coke comes in the furnace, top overall furnace, Fe2O3 enters and some carbon enters. It is the same carbon which enters the bottom part, but as far as iron ore is concerned, it is not Fe2O3, but it is Fe0947. Okay? That is what entering the bottom segment itself. So, the iron ore component has changed. Okay? And we have, for example, as I have indicated, that O by C, O by Fe, this is X, these are different. In the upper segment, O by Fe is 1.5, in the lower segment or the bottom segment it is 1.06, this is 1. Number 2, O by C gas, they are different. The overall parameter and the Oostite reduction bottom segment parameter are different. In one case it is O by C gas, in the other case it is O by C Oostite reduction zone. We will show that the O by C ratio of Oostite reduction zone can be specified, can be given, assigned to a very fixed value based on exact theoretical considerations or relevant theoretical considerations. On the other hand, apart from this, NOB and NGC, these are same parameters. The overall furnace parameters of NOB and NGC apply to both bottom segment as it is. So, therefore, we can now say that NOB will apply as, if you do the oxygen balancing for the bottom segment, then we will write down 1.06 because Oostite enters, it is no more hematite, it is Oostite, and then NaC, the same parameter applies, and then it is going to be O by C gas Oostite reduction zone. The O by C ratio of the gas that leaves the bottom segment Now, let us see what is, do I have enough time? Yes, I think I will have spend about 5-7 minutes time. Now, let us look at, go inside the furnace now and see what happens really. So, if we draw this line and we want to see that how parameters vary, and this is the blast line, below the blast we are not interested, and let us see that this is the height of the furnace and this is. So, we want to plot temperature, we want to plot O by C of the gas as a function of blast furnace height. That is what we are trying to do. Here, if we plot the gas, and we can see here, for example, this is the 1200 and this is the top part of the furnace, and I would say that this is 1000, this is 2000, this is 3000, 1000, this is 2000, this is 3000, this is about 500. So, this is about 2000 Kelvin we are talking about. So, this is Kelvin. We look at the gas temperature first. The gas is at a very high temperature. So, the gas temperature here is 2100 or 2200 Kelvin, okay, at the 2 region. And now, as the gas is ascending, its temperature is going down, it is yielding its heat. So, the temperature goes down and it decreases and it goes something like this. And the gas, as I have indicated, could be somewhere around 500 degrees centigrade, and that is how the gas temperature goes. Let us, we have no solid here in the 2 region, mostly liquid. So, if we assume that solid, it is a solid liquid temperature or non-gaseous species, then the temperature is going to come out to be something like 1000. So, it is 1500 degrees centigrade here, and then we will see that the solid temperature goes something like this. And that is, the white line is the solid line, okay, and then this is the gas line. Similarly, if you plot the O by C ratio in this term, this is a very interesting point of the blast furnace operation, of large industrial blast furnace operation. Then we will see that here what happens is the O by C at this part I will say is 1, okay, and O by C is equal to 2, because that is what the O by C is going to be varying. Okay. So, the O by C from here it gradually is very intense temperature, no carbon dioxide is stable. So, from here it goes something like this, and then it goes something like it, and then it further goes something like this. That is the profile, which essentially tells us that O by C here, for example, this value is something around 1.3, and this is the O by C of the exit gas. So, as we look at the first graph, we can see that the gas and the liquid or the solid temperature varies, but there exists a region in the blast furnace. You can imagine that the gas and the solid, they are moving in opposite directions. So, there is a likelihood that in some region the gas and the solid will come to thermal equilibrium, they will attain, because the gas from 2100 degree it will come down to 500 degree Kelvin, and this liquid solid or solid plus liquid, the other phases combined, they will come out from the room temperature of 300 Kelvin to about 1500. So, in the process of ascending of the gas, and the descending column of the material, at some point they will come to almost like an identical temperature and nearly identical temperature, and this temperature is the 1200 degree centigrade. And at 1200 degree centigrade, there seems to be thermal equilibrium between the ascending column of the gas and the descending column of the solid material. And at that particular temperature, because the pressure is also fixed, so therefore you can understand that this reduction reaction which is taking place per mole basis, I am writing again 1.06 CO2. This reduction reaction which is taking place, since the pressure in that particular region is fixed and the temperature is, gas and the solid have the same temperature of about 1200 degree centigrade, and that is manifested with a O by C ratio of 1.3. What does that O by C in the carbonaceous portion essentially indicates? That if carbon monoxide percentage is 70% and carbon dioxide percentage, volume percentage is about 30%, then the O by C ratio calculated will come out to be 1.3, which is constant. So, because there is a thermal equilibrium between Woodstite, which is the solid descending because no other oxides are there, and because coke is descending as coke itself, it is not taking part in any reaction here except for the gasification reaction perhaps. So, as far as the principal reduction reaction is concerned, iron bearing material is concerned, it is Woodstite which is getting reduced here with carbon monoxide producing iron and carbon dioxide, and that the temperature remains constant. It is pressure is identical, same in this particular region, because in any blast furnace, as a function at a particular height, the pressure at any instant of time, when it is under steady state is going to be constant, it is not varying. So, as a result of which we can conclude that there is going to be a thermodynamic equilibrium or the chemical equilibrium rather of this particular equation at that particular. Now, if we apply the standard equations of thermodynamics, this will come out to be equilibrium constant is equal to PCO2 divided by PCO, and even though total pressure is not 1 atmosphere, it is going to be something different. Okay? If you make that hypothesis that the total pressure comes out to be, PT is taken to be is equal to 1, and then the equilibrium constant is known from the delta G naught is equal to minus RT ln K, delta G naught is equal to minus RT ln K. For that you start reduction reaction ln K equilibrium, and that K equilibrium is equal to PCO 2 by we can roughly consider ignoring the value of 1 point PCO, okay, 1.06. So, we should be able to calculate delta G naught value is known as a function of temperature, okay. The K equilibrium value can be calculated, and this is the total pressure is, if you assume it to be 1 atmosphere, okay, in that case you can get the individual value or the value of partial pressure of carbon or the volume percentage of carbon monoxide and volume percentage of carbon dioxide. So, based on that, one finds out that if we assume total pressure to be equal to 1, this figure essentially suggests that at 1200 degree centigrade, when Woodstite reduction reaction, is taking place, the Woodstite reduction reaction is virtually at thermodynamic or chemical equilibrium, and this is manifested by a constant O by C ratio as I have indicated in this particular figure. This characteristics of a furnace, that you have a stable region of constant temperature, you have a stable region of a constant O by C ratio, is called the chemical and the thermal reserved zone of a blast furnace. And this is a characteristics of all modern large blast furnaces. If the furnace is too small, the gas may be rising very fast, there is no scope to show this kind of a behavior. So, the taller furnace, bigger furnace, giant furnaces will all have the characteristics, thermal, stable thermal and chemical equilibrium zone, and based on this, now we can put this to be equal to gas reduction. So, the carbon, gas which is leaving this is in equilibrium with FeO, and as I have indicated here, that this value can be taken to be equal to 1.3, 70% CO and 30% CO2. And I hope you understood this particular point, that this is based on the consideration that this similar temperature of the gas and the solid phase really corresponds to about 1200 Kelvin, and this, as you apply the thermodynamics, assuming that arc iron is in the pure phase, austenite is also in the pure phase, their activity is equal to 1, and then you can do a order of magnitude calculation or a reasonable estimation of the gas composition, which yields 1.3, and once you substitute that 1.3, because this is the gas which has attained equilibrium chemical composition and then leaving the bottom part and entering the top part, and it is entering the top part with an O/C ratio of 1.3. So, therefore, I can simplify, this is the final statement, I can write the second bottom segment oxygen balance equation as 1.3 NaCe. So, we have now derived two equations. We will continue with our discussion in the next class. I will conclude it, show it in the representation, and we will consider about the third development of the third equation, which will be the bottom segment enthalpy balance equation, which will be not as easy. It is conceptually, this is fabulous. This is, I really like it, the establishment, how systematically one can really show that in big furnaces there is a likelihood of a thermal and chemical equilibrium, and then arrive at, and this is called the austenite reduction zone or the bottom segment oxygen balance equation. This is the beauty of the whole derivation. So, this is going to be generally applicable to all big industrial blast furnaces. Mini blast furnaces, perhaps I have reservation that this equation may not work out so well. Okay? So, we will continue with our discussion.